we were born to tackle some wild arithmetic sequences. I'm telling you, folks, welcome back. And we're going to jump into a very, very special kind of sequences today. But just some real solid review here before we get going. I want to review some terms we want to be very, very, very comfortable with. And the first one says that a sequence, all right, is an ordered blank of numbers. Is an ordered what? Hopefully you can fill in that last blank for me. It's called an ordered list of numbers. It's basically like saying 1, 4, 7, 10, etc. That's what we consider to be a list of numbers that follow a pattern, hopefully, and they're separated by commas. Now, the sum of the terms within a sequence is called a what? Hopefully you just spit out the word series. So basically, if we delete those commas and replace them with a plus sign, and we said 1 plus 4 plus 7 plus 10 plus ... Now adding those terms together would be called a series. Now, of all the series that exist in the world of math, some of the series have very random values. Okay, it just looks like people just randomly pulled these numbers out of the thin air, while others have a very definite pattern, and those are the ones we are concerned with here within our chapter this year. So everything that we do, all the sequences we look at, should have a very definite pattern. Those are the ones we're going to look at. Now, within that world of sequences that have definite patterns, we are going to focus and put a lot of energy into two really special kinds. The first being an arithmetic sequence, and that's what today's lesson is all about. So arithmetic is the first kind. The second really special kind is called a geometric series. And not only is that going to be special this year, but you could ask my Calc 2 students. They also deal with geometric series a lot. So that's a really popular one this year and beyond. Okay, so now we're going to get in and put all our energy into talking about an arithmetic sequence. And this following definition is the most important by far. And again, I encourage you, if I go too fast, just hit that pause button and make sure you get the whole thing copied down. And to really digest this definition and to think about it, rather than just merely copying the words down for the sake of getting your notes done, but really digest what this definition is saying. It says if a sequence follows a pattern of adding, and right there's the key word of the day. That's our buzzword for the day. If we're adding a fixed amount each time from one term to the next, it is called an arithmetic sequence. All right? So this is by far our most important definition of the day, and we need to just make sure we get this entire thing copied down. So if we're adding a fixed amount from one term to the next, this is called an arithmetic sequence. A good example would be to look at the sequence that I had written down on the previous slide. What you'll notice here is to jump from one term to the next. Okay, if you want to jump from the first term to the second term, or from the second term to the third, or from third to the fourth, what kind of pattern are you following? You're adding 3 each time to get to the next term. So we could predict that the fifth term would be 13, the sixth term would be 16, and so on and so on. And we could continue to perpetuate this pattern more and more. Now, what we're adding each time has a very special name. Okay, that fixed amount that we were adding each time is what we call, quote unquote, the common difference. Now that sounds a little funny because difference implies subtraction, and I'm going to run out of room, so hopefully you got that whole word in your notebook. But wouldn't you agree that the word difference, whenever you see the word difference, you think of subtraction? And that is true. I'm not trying to change that idea. But what we're doing is you're taking basically the second term, which up here was the 4, and if you subtract the first term from it, which was your 1, what you get is your common difference. All right, so a sub 3 minus a sub 1. We use the letter D, okay? In the letter D is our symbol or variable that we'll use for common difference, and that's the fixed amount that we keep adding each time. Let's take a look at another example and see if we consider the one on the last slide to be our first example. Let's take a look at the sequence 15, 10, 5, 0, -5, ... So I've shown you the first 5 terms of a sequence, and the first thing that I want you to do is I want you to readily say that, yes, well, if that's the first term, and that's a sub 2, and that's a sub 3, and that's a sub 4, and this one's a sub 5, this is indeed an arithmetic sequence because we are adding a fixed amount each time. And I think this is a really easy one to remember, this rule anyway, because both the word arithmetic and the word adding start with the letter A, so that makes it pretty handy to remember. And then simply the question becomes, what are you adding to each term? Well, we are adding, okay, a value of -5 to each term to get the next term. Or the shortcut, if you ever get confused, you can always do a sub 2 minus a sub 1, which in this case is 10 minus 15. And you'll notice we're getting -5. If we were to say +5, we would be incorrect. So our final answer is we're going to say that D equals -5. That's our common difference. Okay, our next example, I want to try 1 comma 3 halves, comma 2 comma 5 halves, comma 3. There's your first 5 terms. It is arithmetic again because we're adding a fixed amount each time. What are we adding? Well, you can always try a sub 2 minus a sub 1, which in this case is 3 halves minus 1, which gives you an answer of 1/2. Therefore, our common difference, aka the number that we're adding each time, is 1/2. Now compare that to this series, or this sequence. What if I said 1 comma 1/2 comma 0 comma -1/2 comma -1? Okay, another sequence looks kind of similar. Now in this particular situation, if I did the second term minus the first term, I'd get 1/2 minus 1 with an answer of -1/2. So in that case, the common difference would be -1/2, and it's very important that we get the correct sign in front of that number. All right, before we jump into some more examples, there's 2 really important formulas that you need to know. All right, the first one is what I call the rule for the nth term. Okay, and there's other ways that we'll see in the future examples how they might word this. Rule for the nth term. All right, and this is the really important one that we have to memorize. We're going to say that a sub n is equal to a sub 1 plus the common difference times the quantity n minus 1. Now when you look at that, just a few quick clarifications. A sub 1 represents the very first term in the sequence, so that will probably be given to you. D represents the common difference, again, okay, that's just what we've been talking about in the last few slides. That, in other words, that's the number or the fixed amount that keeps getting added from term to term. N represents the number of we'll call it the number of the term you're looking for. So if they want the 5th term, you would just simply substitute a 5 in for that. And then a sub n actually represents the term itself. Not the number of the term, but the term itself. Okay, so we'll definitely practice using that. Now before we go any further, I want to introduce you to the second formula that we're going to need to know. And this is called a formula for finding the sum of a certain number of terms. Okay, the sum of a certain number of terms. And this one looks very intimidating, but I have some good news on this one when I get done writing it. So it says S sub n. Of course, S stands for sum. N represents the number of terms that you want the sum of. Okay, it's going to be n times the quantity, a sub 1 plus a sub n, all divided by 2. And as far as clarification goes, S sub n is the sum of the first n terms. Okay, and of course a sub 1 is the first term, a sub n is the last term, and n itself is the number of terms that were in that pattern. So we'll definitely practice using that one as well. Now the good news is this one right here is going to be on your reference sheet as opposed to this one that was up here. Okay, we really have to memorize this one. Let's put a couple asterisks next to this one. This will be on your next Monday bite-sized quiz. All right, this will be a really important one to memorize right there. Okay, here's a really good example to get us going here. What if they presented us with a sequence 5, 9, 13, 17, ... and they're simply asking us to find the rule for the nth term. So what I'm going to do is I'm just going to refresh my memory, and here's the formula that I had to memorize. The nth term is always equal to the, whoops, I got to erase that, I screwed that up. That needs to be a sub 1. So it'll be the first term plus the common difference times the quantity n minus 1. And so we'll say the nth term is really the first term, which is the 5. Now the common difference is how much you had to add to that 5 to get to the 9. And so I'm thinking, well, I had to add 4, so my common difference is 4, quantity n minus 1. And then what I'm going to do is I'm just going to distribute that 4, and then we'll combine like terms. All right, so we got 4n plus 1, and this is what I consider the rule for the nth term. Now something that's kind of worth noting here, do you notice how similar this equation, for lack of a better word, is to a linear function? I want you to compare that to y equals mx plus b. They're very, very similar. The 4 matches up with the b, the 4 matches up with the m, the 1 matches up with the b. All right, so in other words, here's my little shortcut. The coefficient of n, and this is true for only an arithmetic sequence, the coefficient of n will always equal the common difference. All right, so there's a little bit of a shortcut for you, and that'll be true anytime you're working with an arithmetic sequence. And it has the same influence on that formula as the slope has on a linear function. It's very, very, very similar idea. They're going to increase at the same rate, term after term after term. Okay, our second example now, they're going to ask me to find the common difference, and what they're giving me is the rule for the nth term. They're going to tell me a sub n is equal to 6n plus 3, and there's a really long way and a really short way to do this problem. I'll do the long way first. The first thing you could do is just to start to expand this one out. The first term, substitute a 1, I got 9. The second term, if I substitute a 2, 12 plus 3 is 15, so on and so forth, and what you'll notice is the difference between those two terms is a 6, so I could say that the d, or common difference, is a 6. The shortcut is to simply say what we did on the last slide, where the coefficient of n is guaranteed to be the common difference as long as it's arithmetic. And so we could instantly say that that coefficient is your d value without showing any work at all, as long as you're convinced that it's arithmetic. And we'll talk more later on when we start to mix up the different types of sequences, how to know whether it's arithmetic or not right away. But the long and short of that story is, if it looks like a linear function, okay, if it looks like a linear function, then it's an arithmetic sequence. Here's a little more of a challenging problem. They're asking me to find the 10th term and then the 100th term if the sequence says 3, 5, 7, 9. Now, those are the first 4 terms that were given to us. Now, as far as the 10th term goes, that's not too hard. You could recognize the pattern. The pattern appears to be that we are adding 2 each time. So then I could say, well, let's see, the next term would be 11, and then 13, and then 15, and then 17, and then 19. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I need to do one more term, and it would turn out to be 21. I could say, bingo, there is the 10th term. So that was kind of annoying, but it wasn't too bad. It was very doable. Now, as far as the 100th term goes, you got 2 choices. You could use the same technique I just used and keep adding 2 over and over and over again until you get to the 100th term, or you could write the rule for the nth term, okay? And we could, just to refresh your memory, our new formula looks like this, and then we could simply substitute. Here's the first term. The common difference was 2. And then what we could do is simply substitute a 100 in for n. So we could say a sub 100 is 3 plus 2 times 100 minus 1. And I'm going to go nice and slow here. We'll say, well, that means the 100th term is really 3 plus 2 times 99. Let's see, 2 times 99 is going to be, oh boy, is that 198 must be? So we could safely say that the 100th term is going to be 201. And that's what I consider a shortcut, as opposed to manually finding each term all the way until the 100th term. All right, ready for our 4th example here. They're asking me to find the 7th term if you knew ahead of time that the first term was equal to 3x and the common difference was equal to negative x. Okay, is that enough information to help you find the 7th term? Well, surely it is. The rule for the nth term says you want the first term plus the common difference times the quantity n minus 1. And then, if you want the 7th term, all you have to do is substitute a 7 in for the n's, not the x's, the n's. And so we clean this up a little bit. We'll say the 7th term is really, let's see, Oh, I guess I could have combined the 7 and the 1 right there first. That was kind of a duh. All right, I just had a brain fart, but it doesn't make it wrong, I guess. That gives me an answer of negative 3x. So the 7th term would be negative 3x. And what's so special, I love the nth term because the nth term gives you the flexibility and the overall freedom to go find any term your heart desires. If for some reason you wanted the 573rd term, you could instantly find that with a snap of your fingers by simply substituting 573 in for n. All right, our next example is going to be by far the hardest, most challenging one. And they're asking us to find the 15th term if you knew that the third term, a sub 3, was equal to negative 4 plus 5i, and what if you knew that the sixth term was negative 13 plus 11i, okay? So what's different is if you compare this one to the last example, they gave us the first term and the common difference, which was perfect because that's exactly what I need in order to write the formula for the nth term or the rule for the nth term. Now this one was extra hard because they didn't give me a sub 1 or the common difference, so a little extra challenging. So if I kind of had to make a list of my goals here, the first thing I want to do is to try to find the common difference. And then once I find the common difference, I'm going to go ahead and write my equation or my formula for the nth term. All right, and then I can substitute a 15 in for n. So that right here is kind of my game plan. I'm going to try to find d, then I'm going to write the equation for the nth term, and then I'm going to substitute 15 for n. Sounds easy, right? Well, I wish it was that easy. I'm going to try to give you a visual image. You know, here's our first term, our second term. All right, we know our third term is negative 4 plus 5i. Our fourth term is unknown right now. Our fifth term is unknown, but we do know that our sixth term is what? Negative 13 plus 11i. Now here's where it gets tricky. For now, what I'm going to do is I'm going to conveniently ignore those first two terms, okay? And I'm going to put a box around this. I'm going to put all of my energy into this particular sequence right here. And instead of calling negative 4 plus 5i my third term, I'm going to say that's my first term for right now. There's my second term, there's my third term, and there's my fourth term, okay? And remember that formula, a sub n equals a sub 1 plus d quantity n minus 1. What I'm going to do is I'm going to say a sub 4 equals a sub 1 plus the common difference. Notice I substituted a 4 in for n, so it's going to look like this. And then I could substitute the negative 13 plus 11i in for a sub 4. I could substitute the negative 4 plus 5i in for a sub 1. And then if I simplify 4 minus 1, I get 3d. Now guess what I'm trying to solve for? Yeah, I'm trying to solve for d, and that's why this strategy works so nicely. I'm going to try to add 4 to both sides. All right, and that'll give me negative 9. I'm going to try to subtract 5i from both sides, and that'll give me plus 6i equals 3d. Okay, just to recap what I did, I added 4 over to the other side, and then I took this 5i and subtracted him over to the other side, just kind of simplifying like terms there. And then the last thing I'm going to do is simply divide everybody by 3, and I get negative 3 plus 2i equals d. So that was by far the trickiest thing that we're going to talk about today, and we're definitely going to reference that little strategy tomorrow in class with a few examples. So, but we're not quite done. We have to find, we formed a little game plan earlier in this problem. We said we're going to find d. Now once you find d, we're now going to write the formula for the nth term. So I could now say that a sub n is equal to a sub 1 plus, let's put it in parentheses perhaps, negative 3 plus 2i times the quantity n minus 1. Just remember that we just substituted our d right there. And now, once we write the nth term, they're now asking me for the 15th term, I believe. Let me scroll up and double check before I screw this up. Let's see, where'd that go? Yes, 15th term. Okay, so we need to get the 15th term. We're going to substitute a 15 in for this n. We could say a sub 15 equals a sub 1. Well, Actually, I want to call a quick timeout here. I'm gonna tweak one little thing here for us. I want to scroll back up just a split second. Now, 15. Look at the pattern we had. We kind of tweaked things a little bit, and this is legal as long as we stay consistent. We kind of deleted this term here and this term here. And we said, you know what, let's make what they told me was the third term, let's make that the first term, and so forth and so forth. So if we project this forward, what used to be the 15th term is now the 13th term because we deleted these first two to make our life a little easier. So again, this is legal as long as we're consistent, and we're going to substitute a 13 in down here. So come on down here, and I apologize for that. I want to just fix this. I think this is the easiest way to do it. So that when they say 15th term, that's actually the 13th term, based off of the fact that a sub 1 is going to be, let's see, what did we said negative 4 plus 5i was the first term up there in the red box, plus our common difference of negative 3 plus 2i times, and then we're going to substitute the 13 in for the 1. All right, so we got our hands full here. We're going to start to clean things up. Negative 4 plus 5i. Let's see, this right here is really a 12, so I'm going to distribute the 12 and get minus 36 plus 24i. Combining like terms, oh boy, what's that give me? Negative 40 plus 29i. So it kind of feels like it's the 13th term based off of the red box we had at the top, but it's really the 15th term if you included those first two terms. So very tricky example. I hope you're able to fight your way through that one, and we'll work on those together tomorrow. All right, ladies and gentlemen, we're going to finish with one more example, and they wanted me to find the number of terms in the following sequence. We'll call it 7, 10, 13, dot, 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 55. That's a 55, okay, period. So we have this mysterious number of terms that fall within or in between 13 and 55. I don't know exactly how many terms fall within there. And of course, there's a really long way. If you're really mentally tough and you could fight your way through this, you could list out all the terms. But I'm going to try to show you the most concise shortcut to the answer here. What you do know instantly is you know the first term is 7. You know the common difference is 3 because that's the fixed amount you keep adding to each term. And then we know that the nth term, or the last term here, is a 55. The trick is we want to find the value of n. That's our goal. Can you find n? How many terms are there in this sequence? So recall our secret formula for today. All right. A sub n is 55. The first term is 7. The common difference is 3. And then we have the quantity n minus 1. So at this point, all we've got to do is try to solve for n. So let's see, 55 equals 7 plus 3n minus 3. We'll combine the like terms on the right side. That looks like 4 plus 3n. We'll subtract the 4 over, and then we just got to divide by 3, and I think 3 goes in there 17 times. So n equals 17, and what we're trying to say is that if we started at 7 and went all the way to 55, that's a grand total of 17 terms within that sequence. All right, ladies and gentlemen, hope you had a good time. Let's memorize that formula for the nth term of an arithmetic sequence, and we will see you tomorrow.